Well, we're going to have a look today at the big daddy of confusion in spectroscopic techniques, and that is nuclear magnetic resonance spectroscopy, affectionately and usually not so affectionately referred to as NMR. Now, let's go and we'll explain it as we go, okay? Now, we're doing a little bit of a recap here about what we've looked at previously. First of all, we looked at flame colours and atomic emission spectroscopy, which involved the promoting of an electron, first of all through heat energy to a higher orbital, and then the emission of visible light as that electron then returns from its excited state to its normal ground state. And that little wiggly line there is the light, the visible light being emitted. And remember, this only applies generally to group 1 and 2 metals, okay? So that's the energy we measure, the light energy we measure is as a result of descending from a higher orbital to a lower orbital level. Secondly, we're looking at atomic absorption spectroscopy and UV vis. In those techniques, which we previously covered, we are now talking about the energy absorbed when an electron moves from a lower to a higher orbital level, okay, as we give it either UV or visible light energy to absorb. Thirdly, we looked at infrared. Now this one here is a lower energy level in the spectrum, in the electromagnetic spectrum, and it's not enough energy to change electron orbital positions at all. What it does do, it changes the vibration of bonds between atoms. That means the shake and the rattle and roll kind of thing, you know? That's a big party going on down there with all the shaking, rattling and rolling going on and rocking and so on. Okay, it's just bond energy. Fourth one is NMR, that's the one we're going to look at now. And that is an even lower form of energy on the electromagnetic spectrum, and it affects the magnetic properties of moving charged particles, known as their quantum spin states. Now that sounds all double Dutch, but we'll explain it as we go, and hopefully you'll get a better idea. But first, just let me say that every moving charged particle, that is electrons, protons or whatever, at a subatomic level, they, in so doing, in the process of their moving, they create magnetic fields, okay? Now an example there, I've given you a crude little example there, is just a wire with an electric current moving along that wire. If you get a compass and put it in the vicinity of the wire, you'll notice that it'll flick the compass needle because there is a magnetic field, code B, given to it there, which basically is circular around that wire. So that is what we're talking about. Electricity or moving charged particles create magnetism, okay? You need to get that. Alright, let's have a look at the next slide, and we've got a lot to talk about here. So the very first thing, I'm just going to check them off as we go, and I'll explain things as we go, okay? Now, NMR is used for determining the structure of complex biochemical molecules, okay? So there are two types mainly used, and those types are proton, most commonly used, that means hydrogen nuclei, and also we use carbon-13. Carbon-13 is an isotope of carbon, not very widely appearing in nature, but it still is there. Okay, the normal one is carbon-12, remember? Okay, and there's a reason we use carbon-13, we'll explain that in a moment. Now, the NMR does use frequency in the radio frequency range of the electromagnetic spectrum, the lowest frequency or energy, the lowest energy part of the spectrum. Okay, next point we're going to talk about is that this energy of the radiation is too low to cause electronic, vibrational or rotational transitions. Okay, these are the ones from the flame colours, the atomic emission, the atomic absorption. These ones here are the IR ones. The radio waves, on the other hand, they cause a change in the spin, or that, just read that term to mean the magnetic properties of the particles in the nucleus. Okay, now, to explain all this, we need to understand that at the subatomic level, protons, neutrons and electrons are not just sitting there statically. They are dynamic little beasties, and they are spinning. The whole thing is a moving feast, okay? Spinning on their axes. And all, as I've been explaining just in the previous screen, all spinning charged particles, no matter what they are, they create a tiny magnetic field along their axis. They behave like little tiny bar magnets. I want you to think of them as little bar magnets, you know, like this. They have a north and they have a south, okay, just like a little bar magnet. Now, you've done those experiments in science, haven't you, where you've seen, you know, you put a whole lot of iron filings on a piece of paper and then you get a bar magnet, and you sort of watch the amazing things that happen as the particles of the iron filings all line up along the lines of the magnetic field that's created, making it visible. Okay, well, in the same way, the protons, the neutrons and the electrons can be thought of as having a magnetic field just the same way that a bar magnet does, associated with their spin. It's associated with their spinning. That's why the word spin gets into this, as spin up or spin down. Now, that's just to do with the direction along the axis of the spin. Like the axis, these things are rotating on their axis. These little the nucleons, the protons and the neutrons in the center of the atom, okay, in the nucleus of the atom, and they'll be creating either a spin up, think of that as maybe north up and south down, or a spin down the other way. That would be south up and north down, for example, in accordance with lined up with the axis about which they are rotating. Can you see what I'm trying to say? Yeah, so if you sort of have a little rotation around that away, around their axis, then you'd see you'd either have this magnetic little bar magnet here, where you either have north that way, south that way, or south that way, north that way, depending on which way they're doing it, okay? Now, here this is an important bit. We've done that bit, we've done that bit, we've done that bit. Now, this last bit on this page is pretty important. In many nuclei, the orientations of the spins, of the nucleons, that's the protons and the neutrons, they're paired. In other words, if you tried to line up, have you ever tried to line up two bar magnets so that the both north poles are sitting right next to each other? It's not going to work, because they repel each other and it takes a lot of energy to keep that orientation. So just imagine as the nucleus is filling up with the protons and the neutrons to make it the characteristic element that it is, they basically fill up in a way that they pair off, so that the spin, if the first one's spin up, the next one's going to be make sure that it's spin downs, because that's a nice low energy way to do it. But so in other words, if you only had 12 nucleons, say, in the nucleus, then you're not going to have a net magnetic spin orientation, no net magnetism there, because they've all paired themselves off in a way. You know, the even numbered ones do. But if you have an odd number of nucleons, such as in hydrogen, a proton of hydrogen, or in carbon-13, therefore you will have an overall net magnetic effect or magnetic spin. We use this net spin to help us in NMR. You must have an odd number of nucleons in the nucleus. That's why you can't use carbon-12. Look at the mess I've made of that slide. Oh dear. Oh well, we'll just go on to the next one now. Alright, now, this slide shows you that in the absence of a magnetic field over here, of an externally applied magnetic field I'm talking about here, you have all the atoms are running around with random basically directions of their magnetic field, their spin, okay? Because they're rotating in random directions about their axis, okay? But if you apply an externally applied magnetic field, just the same as if you have a bar magnet with iron filings, you force all the little atoms to line up in the direction of the externally applied magnetic field. Okay, now that's what we do. We apply an externally applied magnetic field. We force them to line up their little magnets, their little directions of spin, so that they're orientated parallel to the direction of the externally applied magnetic field. Now, most of these spins will be aligned parallel. Now, these are the ones that I'm saying are parallel, like this. Okay, that one, and 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 that one. However, that means, now what that means, you don't really have to know this, but I'll just explain it because I'm a curious soul and you might be too. Say that was a north-south orientated magnetic field that you've aligned there. If you're aligning the spin parallel, what's called parallel to the magnetic field, that means that this one would be south and that one would be north, because that takes less energy, doesn't it? Because you try and line them up so the north is aligned with the north. Boy, that's really hard to do. So this is the most comfortable way of doing it. But of course, some of these atoms are going to be a little bit rebellious, and these ones are lined up anti-parallel, so that the norths are lining up with the north of the externally applied field, and the south is lined up with the south of the externally applied field. But hang on, that takes a lot more energy. As I said, a lot more energy. Now, so some of them will at any one moment in time be lined up that way, but it's a constant flip-flop between spin up and spin down, as I call it. Spin up, spin down, spin up, spin down, spin up, spin down. And so that's not static either. They're constantly running around, spinning themselves up and down and all over the place, having a marvellous time. But at any one moment in time, most of them will be aligned with the field. In other words, the magnetic orientation of the way they're aligned will be aligned in a more comfortable way, so that the south is aligned with the north, if you like, of the externally applied field. That's called aligned parallel to the magnetic field. If they're anti-parallel, they're basically taking a lot more energy, and they're aligned in the way that I consider to be like repelling. You know, north aligned with north and south aligned with south. Do you understand what I'm trying to say? Hopefully you do. Now, is all that said in those words below? Let's see. Yeah, in the absence of an externally applied magnetic field, what we're saying is, yes, the net spins and their associated magnetic fields are orientated randomly. Yes, I did say that. But in the presence of an externally applied magnetic field, the net spins and their associated magnetic fields align with the direction of the applied field. Yes. And most align parallel, as I said, with the applied field, but some are anti-parallel. But you've got to get the notion that there's quite a bit of energy difference now between the spin up and the spin down, whereas in the left-hand diagram there's no difference at all. No difference at all between spin up and spin down. It doesn't take any more energy which way you orientate the thing, okay? That's basically what it's all about. Most of this theory you won't need at all, but I'm just giving you the ground rules so that you'll kind of understand what all this abstract gobbledygook's all about, okay? Alright, now this slide, let's get into it. So, in the absence of an external magnetic field, the two states of spinning nucleons have the same energy. I just said that before in the previous screen. Now, but when an external magnetic field is applied, the tiny magnetic field of a spinning nucleon aligns either with the field, which is what I was saying also earlier, lower energy, that's lower energy, or against the field, which is higher energy. So there's now a difference in the energy between the spin up and the spin down states. Are you getting me? Okay, now this is the diagrammatic way below. Here is what I'm showing you, is the diagrammatic way of trying to understand this. You see the direction of the spin, it's like a little global thing like the world, okay, and the axis of the spin is going up this way, like that, and what I'm trying to show you over here is that if you have a look at, there's the two energy levels, okay, the two different energy levels now of the spin up versus the spin down. in the externally applied magnetic field. Okay, now what this little guy is, he's basically aligned with the field so that he's in a comfortable orientation, life is good, and what we've done is we've zapped him with some radio frequency energy. Boo! And what he does is go, oh my goodness, I'm feeling like a vitamin pill's just been injected into me. So he absorbs that energy and goes anti-parallel at the higher energy level after he has absorbed that energy. Now, that's the way it is, okay? But he doesn't stay there forever. After a while he gets a bit dizzy up there and he goes back to his comfortable level at the lower energy level. Oh, I'm getting puffed out. Now, do you see what's going on here? That's what we do. That's what we're exploiting here. In the externally applied magnetic field, there's a difference in energy. There's an energy gap between spin up and spin down. So there's no external field there. In that situation, those guys, there's no energy difference at all between the north being up here and the south being up there, okay? But when you apply a magnetic field, hey, this one here, the norths are aligned, that takes more energy than this situation here where the north is kind of lined up with the south is lined up with the north of the external field, and the north is aligned up with the south of the external field. That's a lower energy state. Okay, and the energy difference, I might as well throw that one in, the energy difference is equal to Planck's constant H times the frequency of that energy which has been absorbed. Okay, and of course it must be a certain frequency, a certain quantum of energy, otherwise no absorption is going to happen, like all this quantum stuff. Okay. Now, did I get that concept across? Hope so. So here's the direction of the magnetic field. There is the lower state, and there is the higher state. And then when the energy is released again, and he thinks, I'm sick of this, I want to go back home, he releases that energy and he goes back to his normal state again. Okay, the lower energy state. Okay, and I did say in the previous screen that slightly more nucleons will be in the lower energy state, aligned with the external magnetic field, which is which state? That state there, okay, the lower energy state. The difference between the two states, which I just covered in the diagram above, is this energy delta E, which is Planck's constant H times the nu, which is the frequency of the energy absorbed in the radio region of the electromagnetic spectrum. Okay, the nucleon can absorb a quantum of energy. It can absorb a quantum. It has to be the right quantum of energy, the right frequency in the radio region, and be promoted to a higher spin level. And when it relaxes back to its lower level, the same frequency is emitted. My goodness, I think we're going pretty well here. Are you hanging on? Are you listening to all this? Because none of this really matters in the end. It's just a matter of how to do the questions that they ask you, and these are not the kind of questions they ask you. So relax, but just try and take it in so you've got enough groundwork to sort of understand what all this stuff really means. Now, this diagram here tries to illustrate what I've just been saying. Now, what is this diagram all about? All right, well, it's really pretty easy. This little section of the diagram here is trying to denote when there's no externally applied field, and they are the two spin states. They are the same energy, spin up, spin down. But then, as you apply an increasingly higher magnetic field, externally applied magnetic field, then the energy between the spin up state and the spin down state gets increasingly more and more difference between the two of them, okay? And this by the way, this mu thing, that's basically saying the spin state, that's mu means spin state, is opposed to the magnetic field, and this spin state here is aligned with the magnetic field. And at this particular level of applied magnetic field, we're saying this gap is the difference between the spin down and the spin up states, okay? And that's equal to Planck's constant times the frequency. But you can see that that gap widens, gets bigger as the magnetic field, externally applied magnetic field, gets bigger as well. You see? Alright, so this is the B applied in this diagram, and that is the gap between the energy levels of those two spin states, which in the absence of a magnetically field, external field, there's no energy difference at all. Okay, am I getting through? Alright, now this is pretty interesting stuff here. The difference in energy of the two spin states depends on the identity of the nucleus, whether it's a proton or whether it's a carbon-13 isotope, and also exclamation mark, exclamation mark, exclamation mark, exclamation mark, the chemical environment surrounding the nucleus. Now, what does that mean? That's a crucial bit. Now, okay, protons in different chemical environments, which means in different places of the molecule, means that attached to different carbons, where the carbons are in different positions in that molecule, those protons have slightly different resonance frequencies. That resonance frequency is the frequency at which it absorbs the radio wave frequency, because of slightly differing electron densities, meaning that the local field is slightly different to the applied field. Now, what that all means, folks, is that what you've got, I'll explain this, I think the next screen tries to explain this more. But look, if every single proton in a molecule saw the same externally applied magnetic field, then NMR wouldn't work at all. But they don't, because there are slight variations within the molecule, for different positions of the molecule, where the electrons, which tend to form a cloud and delocalize and go flying around all over the place, out in the outer reaches of the the orbitals and so on outside the molecule, they don't all just stick to their own nucleus. They form like a cloud, and because you might have some different electronegativities of certain atoms in that molecule. For example, oxygen is very electronegativity. It tends to sort of draw a lot of the electron density of the cloud towards itself because it loves electrons. Okay, and that sort of leaves a bit of a like an ozone layer thing, like a bit of a hole in the density of the electron cloud in some parts of the molecule, and therefore those parts of the molecule get more exposed because these electrons, having their own magnetic field because of they are spinning, they create a magnetic field which opposes the externally applied field. So this gives rise to variations across the geography of the molecule, which then gives rise to variations in the local, quote-unquote, field, the local field that certain protons experience, and therefore that means that the resonant frequencies for absorption of NMR will be slightly different. That's what makes NMR work. This is what gives NMR its effectiveness, because different proton environments can be observed through these different resonance frequencies. Yes, okay, so electron density and covalent bonds tends to shield protons, okay, because it opposes the externally applied field, because they're moving, aren't they? And these shielding effects can be correlated to electronegativity differences, as I said just before, between atoms, between bonded atoms, giving rise to a localized field which is experienced. Okay, are you starting to get this a bit? Hopefully. Now, the chemical shift, that's a big one too, of the nucleus assigns a numerical value to this effect. Now, I'm going to explain that in a moment. Okay, I can't wait to get to the next slide now. The plot is thickening. Now, here's a diagram to try and, my own lovingly prepared diagram to try and explain this to you. Chemical environments of each proton group, and a group means those the ones that are attached to a specific carbon in the molecule, that constitutes a group. They're mostly different from each other because the local magnetic field they see is affected by the rest of the molecule. That is the whole neighbourhood of the whole molecule, okay? Not just any particular electronegative atom, it's a whole range of things. Now I'm showing you some ethanol there, which by the way you should never drink because it's poisonous to your liver. Sorry, I had to throw that in. Now the oxygen is highly electronegative, so it basically sucks a lot of the electron density away from the rest of the molecule because it's really greedy for electrons, yeah? So what happens is you get a big density of electron cloud around it, delocalized electron cloud, and therefore, and the rest of the molecule gets sort of short-changed. They haven't got many electrons around there because the oxygen is so ravenous and greedy for electrons, okay? So that's got a high electron density around there, and that's got a low electron density around there, and this one has got a medium because the lower one's the most exposed to that greedy oxygen, that middle one, that middle ethylene, CH2 group. The methyl group on the extreme left-hand side is not so badly affected because it's a bit away from the oxygen, okay? That ravenous oxygen. So can you see, look, so therefore the moving electrons create their own magnetic fields. Yes, they do, which oppose the applied field from outside and shields the protons, the H atoms attached to the carbons partially from it. So there are three different B local, that's B meaning magnetic field, local environments here for 3 different proton positions. And what are they? Let's have a look. There's number 1, that proton attached to the oxygen. There's number 2, those 2 protons attached to that middle carbon. And there's those 3, position number 3, those 3 protons attached to that methyl carbon, that methyl group. You getting it? Hence, 3 different resonance frequencies, da-da-da-da, and that's why NMR works. That's why NMR works, okay? Pretty exciting, eh? Yeah, 3 different absorption peaks. Let's go. Next one. Now, what have I written here for you? I'm giving you some examples here. Now, what have I got there? Some kind of an alcohol with 2 methyl groups stuck on the left-hand side. So, yes, that'd be 1, 2. What would it be? Oh, it's a type of ethanol. I'd say it's 2 methyl alcohol. Is it? I don't know. Don't count that in case it's wrong. 2 methyl ethanol probably. How many different neighbourhoods are there? Apologies if that's wrong. How many different neighbourhoods are there? There are 4 proton environments. Yes, there are places where they are attached to a carbon or other atom, e.g. oxygen. Now let's just look. 1, 2, 3, 4. But, I want you to think about this. However, 1 and 2, taken individually, are seeing the same overall neighbourhood. They might be mirror images of each other, but they see the same rest of the molecule, exactly the same rest of the molecule, don't they? Geographically they do, okay? So therefore, their chemical environments, in terms of looking at what's the rest of the molecule, are exactly the same, because the rest of the molecule is in exactly the same orientation as they see the rest of the molecule, okay? Now, that means you get 1 peak only from groups 1 and 2, and 1 peak each from groups 3 and 4. Do you see that? They're different. They are the same chemical environment. Those 2 methyl groups on the left-hand side are the same, because the rest of the molecule, as far as they see it, are the same for each other. Yeah, you can look for axes of symmetry to see identical chemical environments. That's the analytical technique. For example, I've shown you the axis of symmetry up there, which means that those 2 methyl groups are actually the same chemical environment. Now here's another one for you. This one here looks like a ketone. So I'm asking you, how many different groups are there, proton environments are there for that molecule? Have a look. Well, I'm saying there's only one. There's only one, similarly to the case we've just considered, because those 2 methyl groups see the same rest of the molecule. If you take each individually, say you were taking that top left methyl group, if you put your thumb over that and then look and see what the rest of the molecule is, and then you put your thumb over the bottom methyl group and see what the rest of the molecule is, you're looking at the same geography in terms of the rest of the molecule, aren't you? So that's what I'm trying to say. They each see the same neighbourhood remainder of the molecule, and therefore there's only one absorption peak for that molecule, okay? Now this situation here shows you what happens when you're looking at a different chemical environment. You see, this was B applied, that was B applied before, but because of the variations, the localized variations within the molecule, therefore you get a slight shift in what different environments observe. So this one here has had a slight shielding from the electron densities that it's experiencing, and therefore its B local is a little bit less than B applied. You see that? Yeah, because the electrons shield partially shield from that externally applied magnetic field. That's what that one's saying. Okay, now let's just push on. This is going to be a long session anyway. So now, to standardize measurements on different instruments under different experimental conditions, we use a reference sample which is tetramethyl silane, okay, TMS, which is basically a central silicon atom with tetrahedral structure of 4 methyl groups around it. And the reason that we use that is because all the hydrogen atoms in the molecule are in an identical environment. If you think about that, there's a little diagram of it down there, producing a single peak of absorption well away from most of the peaks of interest. Yeah. Now, also TMS is chemically inert, so it can be added to a sample without causing interference and chemical reactions. Okay. Now, this point here. The difference in energy needed to change the spin state in the sample is compared to the energy level at which TMS absorbs, and this is called the chemical shift in parts per million. Now I describe that in the next slide. The chemical shift of TMS is defined as 0 because it's taken as the reference point. The symbol Greek little delta is often used to represent the chemical shift. Now, I'll go over this in more detail on the next screen, but a value of 1 part per million would simply mean that the signal compared to TMS of whatever's doing the absorbing, so whatever proton environment is doing the absorbing compared to where TMS is absorbing, is shifted by, say, 200 Hertz of radio wave frequency when you are bombarding the thing with 200 megahertz of radio waves. Okay, now that is in the 200 megahertz is in the frequency of radio waves, so that means if the difference between the absorption frequencies of whatever proton environment you're observing absorption at compared to TMS is 200 Hertz, then we say, alright, that's 200 over 200 million, which would be 1 part per million. And that means when you do it that way, it's independent of the instrument which you're measuring it on. Now I got this out of Wikipedia. It just goes over what I just said. Delta is the difference between the resonance frequency and that of the reference substance, which is TMS, divided by the operating frequency, that's the radio wave operating frequency of the spectrometer. Okay. Now, so they've gone through an example there, and they've gone through exactly what I just said there, except they've used 300 Hertz difference in resonance frequencies compared to 300 megahertz of radio wave frequency to get a 1 part per million chemical shift. Now, and they call it part per million because the fraction that you get is times 10 to the minus 6. Now, this little bit here might be of interest to you. Although the frequency, the difference in the resonance frequencies or the frequencies themselves depend upon the applied field, the applied size of the magnetic field that you're applying, externally applied magnetic field, which by the way is absolutely humongous, because you need humongous magnetic fields to create small, measurable differences in frequencies of absorption. The chemical shift itself, according to this formula, is independent of the instrument. You'll always get the same value. That's why they do it that way. Okay. On the other hand, the resolution of NMR will increase with applied. The resolution of NMR will increase with applied magnetic field, resulting in ever-increasing shift changes. Yes, it will, but we won't worry about that for now. Okay. We've covered what chemical shift is, and we've told you that it's basically independent of the instrument and it's independent of what the applied magnetic field of the instrument that you are using. Okay, all right. Let's keep going. I'm starting to get tongue-tied. Now, the instrumentation. All right. Now, this is really interesting. If you've ever seen this instrumentation, it's amazing. Like the NMR machine itself is like the size of a fairly large domestic water tank, and I mean a large one. It goes from floor to ceiling. It's highly magnetic. They use liquid helium coolant with metal in the magnets to create superconductors. It's really high tech, and it's just amazing stuff. And you better not go in there with your credit card in your pocket, because it's going to get zapped because they're so magnetic. So, alright, NMR spectrometers include a radio transmitter, so that's where you get your radio waves, a very powerful magnet to produce strong magnetic fields, and a sample is placed in a glass tube at the very, very top part of the tank, and it spins, so that the rest of the test material is subject to a uniform magnetic field. Solid samples are dissolved in a solvent that will not give a signal. That's interesting. Usually they don't use water, by the way, in proton NMR. They use D2O instead of, that's deuterium. There's hydrogen, deuterium and tritium are the isotopes of hydrogen. So they use this expensive water called D2O because that has an even number of nucleons in its nucleus, so therefore you don't get any spin from it. Imagine using water. You just completely sabotage yourself, because that stuff's going to have all kinds of interference with the absorption going on. And you have a radio receiver which detects the radio frequency emitted as the nuclei relax to their lower energy level, and you have a computer which records the whole thing. Where would you ever be without computers? Now, alright, we're going on and on and on. Now here's proton NMR. Now we're starting to get to the business end of this, the types of questions you're going to get asked. Proton NMR is used to identify the number of chemically distinct hydrogen environments there are in a molecule. You have two kinds, low res and high res. Now low res is what we've been just talking about, where the number of peaks is equivalent to the number of different carbon bonding environments experienced by the hydrogen nuclei or protons in the molecule. Now this is important, the relative area under each peak is proportional to the number of hydrogen atoms in that particular group or environment. Okay, so you can see here in this example, if you look for lines of symmetry here, I can see this guy and this guy are the same, because they see the same rest of the molecule if taken individually. So I reckon there are two environments there. Those are the same, and then you've got this one. And there's TMS, and this one belongs to those 6, and it's got a higher area than this one, which belongs to those 2. Okay, you get it? It's easy, isn't it, when you really look at it that way? Now let's have a look at this little one over here. How many environments we got, folks? I think I've already talked about this as an earlier example. Look, there's only one, because they both see the same different rest of the molecule. So there's your TMS and there's your absorption peak. Voila! Does it make a bit of sense now? Hopefully it does, because it can be very confusing stuff. Now this stuff here, I'm not going to dwell on this. This is from, this just gives you some examples of where these things are highlighted in red. That tells you protons in different kinds of environments in molecules that might be observed, and their associated chemical shifts that you might be seeing in parts per million. Okay, and you can quote these in parts per million because they're independent of the machine they're tested on if they are in those units of parts per million, as I described earlier. All right. See, this is interesting, isn't it? See that little beastie there, that benzene molecule? Those protons are all the same environment. All the same environment. So, all right, that's that side of it. I'm not going to keep going on about that. Now, this is the other side of the coin. This is high resolution NMR. This is a little bit crazy, this one. Now, on closer examination, NMR peaks, if you zoom in on them and magnify them, you can see that there's also additional more fine detail. They start to split these peaks, and this is because of magnetic interactions between protons, adjacent group protons in the next door, immediate next door neighbour group, because in chemically non-equivalent environments. This is known as spin-spin coupling or splitting, and I'm going to explain this in a minute. In ethanol, for example, the methyl signal appears as a 1-to-1 triplet, and with an area or integration of 3 for the 3 protons, and a methylene or CH2 as a 1-3-3-1 quartet. Now that all seems like it's double Dutch, but look, I'll explain it over the page in the next slide. This arises because protons in an externally applied field themselves behave like tiny bar magnets because they're all spinning around the place, and they affect their near neighbours. So this stuff here is to do with the slight variations in the magnetic field observed by a proton because of its immediate next door neighbour, not the electron shielding. That's all basically the low res stuff. This is finer detail again. Now you can see that the methyl signal in isopropanol, for example, is a 1-to-1 doublet. Don't worry about that for now. I'll talk about it on the next page, and you'll see what's going on. This one here is a triplet, so it goes on, and this rule comes into play now. This is the n+1 rule that says that the NMR signal for a set of chemically equivalent protons with n equivalent but different near neighbours will appear as n+1 peaks. Well, that was some double Dutch, wasn't it? I'll show you. All will be revealed. Here we go. Next screen. Now, this is my own creation. Now, just check this out. This is some maths we're going to do now. We've got some ethanol here. Now, I want you to think about this CH2 group, okay? Now, these protons are going to have their own little spin-up, spin-down party, and that's going to cause variations in what these guys over here are observing as their B local, because these CH2 guys are basically affecting what they see by their own little variations in magnetic fields they're creating. For example, you see those CH2s there? Now, you think about this, there's 2 of them. So what states could they be in at any one time? They could be both spin up, or they could be both spin down, or you could either have spin up, spin down, or spin down, spin up. Now that's all you can have. But you can see, therefore, and they're all spinning up and spinning down and changing and flip-flopping and having a marvellous time all the time. It's not a static situation, it's totally dynamic. So therefore, you can see that this configuration here is twice as likely as that configuration or that configuration. So in terms of probability, you're twice as likely at any point in time to have that configuration of one up and one down as you are to have both up or both down. So therefore, these 3 poor old confused little beasties over here, they see a splitting in what they're observing. Their resonant frequency is split in accordance with exactly that configuration that I've just described over there. In terms of any one moment in time, they are seeing the variations, localized variations, caused by the antics of the CH2 group next door. It's changing the magnetic field that they observe in exactly those proportions, because the proportions correspond to the probability of what's being observed in terms of spin-ups and spin-downs at any one particular instant in time. Okay, now I'm just going to rub out some of this because I'm creating a huge mess. Now, okay, now let's now consider. Oh, sorry, that's no good. Now consider these three, these guys here, the CH3 group, and what they do to the CH2 group. Well, there's three of them, so they could be all up or all down, or you could have three ways of having two up and one down, and you can have three ways of having one up and two down. So therefore, that's all the permutations and combinations of spin-ups and spin-downs you can have for those three protons. And in the same way that I just described earlier for what's happening with the CH2 group, you get this probability of what's going on with those three protons in terms of their spins ups and spin downs at any one particular point in time, which creates that probability diagram, which is what these guys here, these CH2s, observe as their localized field, because it's being upset by the antics of their next door neighbours, the CH3s. My goodness, what a zoo. So there it goes, and that's how it all works. It's just as simple as that. Now, incidentally, the OH, he's a loner, that guy. He doesn't, if he's attached to an oxygen, he doesn't split and he doesn't cause splitting. And why that happens is well beyond the scope of this course. I can't stand all this mess, so I've got to rub it out. Okay, now that was all that. Now, we've already gone up to 48 minutes, so I hope we get this finished very soon, because I'm going to collapse. Now, okay, next screen. Alright, now, that screen there is now describing beyond. Okay, now this one here was the externally applied magnetic field, and you will note that we varied that by the effects of the electron cloud density and variations thereof to something a little bit lower than B applied because of the electron shielding. And now that's that black dotted line. Now we're now saying that those localized fields are further modified in accordance with the spin-up, spin-down antics of the immediate next-door neighbours of any proton group. That's what we're saying. Okay, that's the fine resolution of the spin-spin coupling or splitting. We're nearly done now. Now, okay, let's look at some ethanol here. We've got three environments as we described. We've got the CH2s, and this is low res now. This diagram is still low res. We've got the CH3s and more of them, so it's a higher area under the peak. They call that area under the peak integration. And we've got the OH group. Now, if you further look at this, ladies and gentlemen, you will see. Watch this. This is the peak of the CH2s. Now that's split into 4, and that tells you that this next door neighbour must have 3, because those 3 protons had 4 different permutations of spin-ups and spin-downs. So that tells you that guy's got 3 in it, so it's obviously got to be CH3. Now if you look at, wait till I just get this, clean this up a bit. Now if you now look at this particular one here, this one, that's basically split into 3, and therefore that tells you that this one must have had 2 in it, so therefore that's going to be CH2 basically. So in order to work out, it's kind of like you've got to look at the other one. If this is split into 4, the other one had 3. If this is split into 3, the other one had 2. So this is where this n+1 thing comes from. It's just maths. It's permutations and combinations of all the antics of the spin-ups and spin-downs that these guys are getting up to, having a marvellous time down there at a subatomic level. So that's where the n+1 thing's coming from. You look at the environment, you see how many peaks, and you say, well, that's n+1 as many protons as this guy's got. That's what you do. Okay, that's how it works. That's how it works, okay? Let's get out of here before I completely collapse now. Right, now, this is the last bit now. Thank goodness, this is easy to explain. This is carbon-13 spectroscopy. Now, carbon-13 is also a naturally occurring isotope of carbon. This is not proton. This is a whole new area of spectroscopy now, but the same principles apply as to the proton environments, except we don't care about the protons. Now we're just going to use the carbons themselves, the positions that they are in the molecule, the carbon-13s, okay? So it does have a nuclear spin, yes it does, because it's an odd number of nucleons in the carbon nucleus. Nucleons meaning protons and neutrons, by the way. It is used in NMR spectroscopy to identify different carbon environments in the molecule, yes it is. The chemical shift from the TMS reference is dependent on a carbon atom's environment. In other words, what is its neighbourhood? That's all you care about. What is its neighbourhood? Look at the whole neighbourhood, okay? The chemical shifts are much bigger than for proton NMR. They go from 0 to 200. Yeah, they're different from proton NMR, which goes from 1 to 12 typically. Peaks in the spectrum. Now this is good news, isn't it? This is why they never ask you any exam questions on carbon-13 NMR, because they're always a single line. There's no spin-to-spin coupling, at least not within the scope of this course. There isn't, and also, so it's always a single line. So that's why it's a bit too easy for them to set you a question. Okay. Alright, what else? Yeah, the peak areas are also not indicative, so that's funny, isn't it? You don't get any indication from the peak heights as to how many carbons there might be causing that peak, so it doesn't make any difference. And as I said, the spin-to-spin coupling is not important, okay? It doesn't work that way, so you don't look at high-res carbon-13 NMR. Alright, one example, then I'm having a cup of tea and going away. This one will be proton NMR. Proton NMR spectrum of a compound. Now, they're telling us it's C4H8. That's pretty interesting. C4H8. Now, what are they asking us to do? Find this from the spectrum, record the following data from the table. Yeah, from your table. The table that I showed you earlier, but we're not even going to do that. Alright, so the number of peak sets and hence the number of different environments. Well, here's your TMS. There's 2 different peak sets. So there's 2 different proton environments in that molecule. Now, the relative number of protons in each peak. Well, that's got a peak area of 1. This has got a peak area of 3. So that's telling you that this guy here has got 3 times as many protons in it as this guy here. That's what that's telling you, because it's relative peak areas, okay? Now the fine structure. Well, I'm going to take a punt. I'm going to say, look, this is C4H8, which I happen to know is the generalized formula CnH2n for an alkene, right? It's an alkene. So I'm looking for a double bond somewhere. There's going to be a double bond in this. And let's see. Now this, let's try and work out what it looks like. This guy here is being split into 4. So this guy here has got 3. That's what that tells you, okay? This one here, this guy here is split into 2. So this guy here has got 1. So I think I can just about get this. See, if I consider 3 and then 1, that makes up 4, doesn't it? So, and they're identical environments, so I think I've just about got this. Look, you have a look at this. CH3, CH would be what's going on there, okay? One's got 3 in it, one's got 1 in it, and the whole, but what the molecular formula is double that, and we're looking for a double bond and identical environments. So I think I just do this. CHCH3, and I think, by George, I think we've done it, because that's the same environments, they're the same environments, they're the same environments, there's one double bond, alkene, and these environments correspond, these peaks that we've observed, and I've completely destroyed with all my rambling drawings here. Quick, clean it up. That would correspond to what we've got there, yeah? That would correspond, because that little guy there that means he's got 3, which is this one, and this one here that's got split into 2, it means this one here is 1, which corresponds to that one. I think that's the answer. I think that's the answer. In fact, I'm sure it is. Let's see. Yep, it is. How marvellous. And I think That's the last slide. Well, boy, that was a marathon, wasn't it? So, yeah, and that's all the stuff. So we'll just quickly run through it, and then we'll go. Okay, so what are we saying? Atomic nuclei produce a magnetic field as a result of proton and neutron spin. The nucleus will always have an overall spin when the number of protons plus neutrons is an odd number. That's good. The interaction of an external magnetic field with the magnetic field of the nucleus of an atom is used in NMR spectroscopy to determine the identity and structure of a compound. That's done. Okay, the third one, the magnetic fields generated by nuclei align with or against an external field. Nuclei aligned against the external field are at a higher energy level than those aligned with the field, yes? Electromagnetic radiation in the radio frequency range causes nuclei to move to a higher energy level, yes it does. The external magnetic field experienced by an atom within a molecule is modified by the magnetic field of neighbouring atoms. Yeah, the electronegativity story, okay? Now, the energy required to excite a nucleus of an atom to a higher energy level depends on the arrangement of the atoms within a molecule, the atom's environment. Yeah, we knew all that. Each peak on an NMR spectrum represents a different chemical environment. Yes, it does. It definitely does. And the area under each peak indicates the proportion of atoms in each environment. That's for proton, not for carbon-13. The frequency at which a nucleus absorbs radiation relative to the absorption of the TMS standard is called the chemical shift, and the chemical shift is characteristic of an atom's environment. It is. The peaks in high-res NMR, proton NMR, may be split into clusters of peaks. The amount of splitting provides information about the number of hydrogens attached to the adjacent carbon atoms. The interaction between protons and adjacent atoms that causes the peaks to split is called spin coupling. And lastly, the analysis of NMR spectrum involves consideration of the number of peak sets, the chemical shift of each set, the relative area under each peak set, and peak splitting. And I feel like I should have a splitting headache, but I don't get headaches, so I'm really lucky like that. Okay, we did it in under 57 minutes. So thanks everybody, and see you.